tank containing a liquid at a temperature well above its boiling point at normal atmospheric pressure fails, a special type of explosion occurs. The phenomenon is known as a Bleve, a boiling liquid expanding vapor explosion. In the late 1960s and early 1970s, a number of firefighters and others were killed or injured in accidents involving liquefied flammable gases. Firefighters arriving at the scene were often faced with raging fires around tanks whose contents and conditions were not always apparent. In more than a dozen incidents worldwide, over a 15-year period, close to 100 people were killed and many more injured. The Bleve phenomenon, once a technical footnote in fire science textbooks, became the focus of a major national effort to make the transportation, storage, and transfer of liquefied flammable gases more safe. Liquefied gases are as much a part of American life today as they were in the mid-1970s. Used in a wide variety of industrial, agricultural, and residential settings, they play a critical role in heating, transportation, and many industrial processes. Of all liquefied gases, propane, which is one of a family of flammable liquefied petroleum gases, is by far the most common, with over 20 million installations in the U.S. today. To distribute propane and other LP gases such as butane, methane, and vinyl chloride, a vast network of storage and transportation facilities exists. These consist of pipeline terminals, regional and local distribution centers, as well as large fleets of highway cargo tanks and pressure rail tank cars. Yet despite the widespread use of liquefied flammable gases, the incidence of Bleves and the number of injuries and deaths resulting from Bleves have decreased markedly in recent years. One reason is the improvements that have been made to the equipment used to store, transfer, and transport LP gases.
When they've Bleved and they've died from burns.
Another reason is the increased awareness of the Bleve hazard on the part of regulatory authorities, industry, and emergency response personnel. But while the likelihood of Bleves and injuries and deaths resulting from Bleves were dramatically reduced, Bleves still did occur. In a rural area near Murdoch, Illinois, 7 tank cars derailed. Spilled chemicals ignited, engulfing other tank cars carrying LP gas. Firefighters responded quickly and a civilian evacuation was ordered. Having limited water resources, attempts to control the fire were unsuccessful, and firefighters too retreated. Around dusk, the first LP gas tank car Bleve. That night, a second tank Bleve. While no one was injured in this accident, the explosions left a graveyard of scattered, burned-out tank shells. One tank section had rocketed more than 3,500 feet. In Woodruff, Utah, a truck plowed into a propane storage facility, causing the Bleve of an 18,000-gallon tank. An adjacent 30,000-gallon tank, weighing almost 100 tons, was knocked 35 feet from its support and burned through the night. By morning, the damage could be assessed. Smaller sections of the 18,000-gallon tank had traveled over 500 feet. The largest section damaged nearby buildings and vehicles before coming to rest a half-mile away. In Orlando, Florida, a fire started at a company that distributes flammable and other industrial gases. Cylinders in an outdoor storage area were exploding as firefighters arrived. Larger storage tanks were threatened, and flames had already spread to adjacent properties. The area was quickly evacuated. Heavy water streams were used to control the multiple fires and cool the remaining tanks. By the time the fires were extinguished, 5 hours later, more than a half-dozen properties had been damaged or destroyed. To deal effectively with potential blevies, it is necessary to understand something about liquefied flammable gases and the vessels used to store and transport them. Unlike gasoline and home heating oil, propane and other LP gas fuels are gases at atmospheric pressure. For economy of storage and transportation, propane is liquefied through a process of pressurization and cooling, reducing its volume 270 times. Vessels used for the storage and transportation of liquefied gases must be capable of maintaining the pressure needed to keep these gases in their liquid state. To meet this strength requirement, most pressure vessels designed for LP gases are of welded steel construction, with tank wall thickness, in the case of rail cars, typically greater than 1/2 inch. All pressure vessels are equipped with safety relief devices designed to relieve pressure caused by overloading, extreme ambient temperature rise, or fire exposure. In rail cars, they are housed in domes that also contain the connections used in loading and unloading operations. When properly loaded, tanks are never completely filled with liquid. A vapor space is always left at the top of the tank to accommodate additional vaporization resulting from normal temperature increases. All containers and other hardware used in the transportation and storage of liquefied flammable gases are subject to strict manufacturing and operational guidelines, and under normal conditions do not present special risk. In an accident situation, however, especially one involving fire, tanks containing liquefied flammable gases can be particularly hazardous. Analysis of experimental data and study of actual incidents have resulted in a clearer understanding of the mechanics of a bleve. While bleves have been known to occur in tanks weakened by physical damage, such as from an accident, most bleves result from fire exposure. When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning. Once the causes of Bleves were better understood, several important steps were taken to reduce the risk. The area most affected was rail transport. Railroad tank cars carrying liquefied flammable gases are now required to have thermal protection to prevent direct flame contact on the tank. On most cars, this takes the form of a flame-retardant blanket wrapped around the tank shell. This protective barrier, under test conditions, will keep tank shell metal at a safe temperature for 30 minutes when exposed to a torch fire, and 100 minutes under pool fire conditions, adding critical time for evacuation and other emergency response measures. The thermal protection also lessens the severity of a Bleve. With vapors venting over an extended period of time, there is less fuel in the tank at the time of failure. On some tank cars, in addition to thermal protection, insulation is also applied. This layer moderates product temperature shifts as outside temperatures change, but is not designed to provide tank protection from direct flame exposure. Both the thermal barrier and insulation will be protected with a metal jacket forming the outer surface of the tank. Another approach to thermal protection involves the application of flame-retardant materials sprayed directly onto the tank. This was the method used to retrofit older tank cars and is still used today. Rail tank cars intended for LP gases have seen other improvements as well. To better protect tanks from puncture, tank ends are now fitted with an additional layer of steel called a head shield. This half-inch plate, shaped like the tank end, is intended to absorb the impact of a collision, protecting the pressure vessel inside. To further improve tank safety, cars carrying liquefied flammable gases are now equipped with shelf couplers that reduce the likelihood of punctures from both collisions and car separations in a derailment. Without shelf couplers, tanks can be punctured in a collision or derailment. With shelf couplers, the likelihood of this type of accident is reduced. Should cars collide, however, head shields provide protection in the area most vulnerable to puncture. This is the type of head shield that was used to retrofit older tank cars, and it is still in use today. Train collisions and derailments weren't the only setting for Bleves prior to the 1980s. Bulk storage and distribution facilities also saw their share of serious fires and explosions, resulting mainly from pull-away accidents during transfer operations. Today, large liquefied flammable gas facilities incorporate a variety of safety devices that prevent large releases of gas that might ignite and threaten other tanks. LP gas facilities with tanks over 4,000-gallon capacity are now equipped with emergency shutoff valves. These valves close automatically when a sensor at the loading point is exposed to fire. They can also be manually operated, both at the loading point and from remote locations. Tanks are equipped with internal excess flow and backflow valves that also limit fuel release from breaks in hoses and piping. Some large facilities are also equipped with flame and gas detectors that can automatically interrupt the fuel flow and sound an alarm. In addition to systems that limit accidental product release, many tank installations are equipped with heat-activated water deluge systems capable of keeping tank metal cool in the event of fire exposure. Fixed water monitors at some distance from the tank accomplish the same task and have the added benefit of being less subject to damage from a vapor cloud explosion. But even with the best procedures and the finest technology, accidents still occur. And when they do, firefighters encounter one of the most dangerous situations they will ever face. Ignition of propane from a hose rupture during transfer operations resulted in a fire at a propane storage and distribution facility in a populated area of Colorado Springs. The facility consisted of 5 horizontal storage tanks ranging from 2,600 to 18,000 gallon capacity, plus over 1,000 smaller tanks of varying sizes. When firefighters arrived, small cylinders were already exploding, and large storage tanks had begun to vent, sending torch-like flames over 70 feet in the air. Fearing larger explosions, a decision was made to attempt to cool the bigger tanks. Unmanned water streams were set up, and firefighters retreated to safer ground. An evacuation was ordered for an area 3,000 feet around the site, and hospitals and other emergency personnel were alerted for a possible disaster. By evening, the situation had been stabilized enough for firefighters to enter the site and shut off fuel supply lines. Small fires and venting relief valve gases continued to burn through the night, although there were no additional blevies. By morning, firefighters could re-enter the site, deal with the residual fires, and inspect the remaining tanks for damage. Through the effective use of equipment and personnel, a disaster had been averted. Given the variety of circumstances and situations that can lead to blevies, what can firefighters do to prepare? Become familiar with and develop response plans for facilities where propane and other liquefied gases are stored and used in your community. Identify how liquefied gases are transported and when and where they are shipped. Know what questions to ask if you encounter a tank involved in an accident. What is the content of the tank? Is there a fire, or is there leakage which could result in fire? How long have the tanks been exposed to flame? Blevies have been known to occur within minutes of an accident, and in other cases, not for days. Is the relief valve operating? The high-pitched whistle from a pressure relief valve is a sure sign of pressure buildup, but it will not tell you when or if the tank will blevy. Is there sufficient water supply to keep tank metal cool for an indeterminate length of time? It is estimated that 500 gallons per minute is the minimum required for each point of flame impingement. Do you know enough about the condition of the tank? Blevies have been known to occur in tanks that have been weakened from physical damage, the result of an accident, for instance, or even stress from attempts to move a damaged tank, or metal weakening from corrosion or pitting. That's why cleanup operations and the handling of damaged tanks should only be conducted under expert supervision. Should you even attempt to fight the fire? Is there a threat to life and property that justifies exposing yourself to the devastating effects of a blevy? While government and industry efforts have proven effective in reducing the number of blevies, extreme caution must still be exercised during incidents involving fire and pressure tanks. Firefighters must recognize that despite their best efforts, even following recommended procedures, they may not be successful in preventing a Bleve.